Hello friends and neighbors, time for another networking video. Today we're going to talk about switching, spanning tree, VLANs. Oh my. Actually, we're going to do that in a series. How about we start with a little trip? Come along with me back to 1990. Back then, the world was operating on a standard called IEEE 802.1d. So 802.1d is where we get all of our stuff about media access control bridges. It's where we get our ideas for how they operate, the access method that they're going to use, carrier sense multiple access with collision detection, how they do their learning, pick up the MAC addresses to put in the source address table, how the frames are processed, priority handling, the error calculations. That's not only the frame check sequence, but whether or not a frame is going to be dropped. All the reserved addresses, in this case we might be talking about those reserved for broadcast, or all of those multicast addresses begin with 01, including spanning tree, and lots more. So if you want to learn how a switch actually operates, that's the document to go to. Chapter 4 is entitled The Spanning Tree Algorithm. Here are a couple of graphics right from that show you how nodes are connected to a bridge, and then how bridges interconnect LAN segments. That's just a section of figure 3.1. All right, so let's go back just a little further to 1985. While working at DEC, Radio Perlman wrote a paper on the algorithm, that is the spanning tree algorithm. An algorithm for distributed computation of a spanning tree in an extended LAN. The story goes that not only did she go home for the weekend and solve the problem of imposing a tree-like structure on a looped Ethernet structure, but had time enough to write a poem about it. Algorime. I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the route must be selected. By ID, it is elected. Least cost paths from route are traced. In the tree, these paths are placed. A mesh is made by folks like me. Then bridges find a spanning tree. I know, you're all giddy right now. You're all worked up. So let's talk a little bit about spanning tree. So this will be a little bit of review. We're not going to cover all of the things that maybe we did in some of the other videos or in the chapters. So the whole point of spanning tree is to put a tree-like structure onto a topology that might have loops, but those loops are not completely severed, right? We still have the ability to get blocked paths reactivated. So the ports are blocked, they're not dead, and that gives us path redundancy. It takes a long time, but it gives us some redundancy. Now, why do we want to get rid of loops? Well, if you have broadcast traffic that is continuously circulating, that's bad. It eventually consumes all of the bandwidth. We've done this in labs. It's kind of fun to do, but it kills the network real quick. The other thing is that if you have a loop structure, MAC addresses appear on more than one port, so that's also a bad thing. So once the protocol is running, and it's running by default on all switches, right? The switches exchange bridge protocol data units, or BPDUs. And the BPDUs are there to do a couple of things. They elect a root bridge, and then they elect a designated bridge for each segment, and then they eliminate loops. And the way that we eliminate loops is we block ports. Now, how do you know you have a loop? You know you have a loop is because a switch will receive a BPDU on more than one port with the same root ID advertised. So instantaneously, the bridges know they have a loop. It uses a special multicast frame beginning with 01. Each bridge or switch calculates the shortest distance to the root. That's the idea. It is a tree of shortest paths. And then we also include the port information because, as we'll see here in a little while, sometimes the comparison algorithm needs to go all the way down to the port information. Here is a bridge protocol data unit. There's so many exciting things to look at in one of these. But I'll point you at a couple of things. One is the flags. Now, the early 802.1d spanning tree doesn't really do too much with these flags. There's just a couple of uses for them: topology change or not topology change. The red box in the middle, the big one, those are the 4 fields for our comparison algorithm. Those are the really important ones. So we have the root ID, the root path cost, the bridge identifier, or maybe more accurately, the transmit bridge ID that this particular BPDU came from, and then the port ID. Now, in the case where the root ID and the bridge ID is the same, as is the case here, you know that this came from the root bridge. In the bottom red square or red rectangle, we have the timers that are associated with a spanning tree, and those become important to us later on. So those, again, are the 4 ports that we use in the comparison algorithm. And so what happens is when you are comparing BPDUs and you're trying to determine what ports to block, the first thing you do is you compare root IDs. And really what that's for is the election of the root bridge. The one with the lowest priority map becomes the root. And then the path cost is the comparison. So you got 2 BPDUs, you're trying to figure out which one is the best way, whichever one has the lowest path cost. If the root IDs and the path cost are the same, then you take the best transmit bridge ID, and the best transmit bridge ID is the lowest transmit bridge ID. Same thing with the port ID if you need to. So that's the idea. The switches and ports also have roles within the topology. So we have root switches, and pretty much everybody else is a designated switch. Root ports receive BPDUs. They also point the direction of the root. And then designated ports generate BPDUs, and they point away from the root bridge. So there's our terms, right? We have root bridge and designated bridge. Designated bridge is any bridge other than the root that has traffic flowing through it on the way to the root. We already talked about root and designated ports. All of these are indicators of where you are physically located inside the topology. Now the states are ports. All ports come up blocking. This is why when you plug a node into a switch or when you turn on a switch, all the lights come up amber. They're not green yet because the switch is going through spanning tree discovery. It's trying to figure out what to do with the ports. So we don't come up forwarding, we come up blocking. And it takes 30 seconds. Why? Because you're 15 seconds in the listening state, and then you're 15 seconds in the learning state, and then finally you go forwarding. So 30 seconds always. You can set your clock by it. Disabled is another port state, but it's not really part of spanning tree. It's really shut down. Here is some sample output of the show span that you get on a Cisco switch. You can see at the top that we're talking about VLAN 1. We see the root ID. The root ID is a combination of priority plus MAC address. So it's those 2 fields, 32769 plus the MAC address after that. The cost per port, and then this particular port that the information was received, and then there's our timer values. Down at the bottom, you can see some of the port states. This one, I happened to catch this one when ports were going through learning and listening states. And then you can see the priority and number, 128.14 and 128.15. Those are the port IDs. So it's the port priority plus the port number. On the right-hand side, we see that the ports have all gone forwarding. We can also see that these are P2P. These are point-to-point ports, meaning that they're interconnecting switches together. Let's see. We also have, right, so this is another good thing to point out, that the root ID in this case is different than the bridge ID, which is a little bit lower than that. And this is an indication that we're not sitting on the root bridge. The last thing that I'll point out to you is the role of the ports. We see that they are root and designated. So the way that we start all this is that each switch begins by assuming it's the root. And it assumes that until it hears a BPDU with a better root ID. And then things turn around. All switches eventually agree on the best route, and they all advertise that route in the BPDUs. And then eventually, based on the comparison algorithm, we end up blocking ports. So you go down root ID, path cost, transmit bridge ID, and transmit port ID until all the ports that need to be blocked are blocked, and we've eliminated all the loops. If there's a failure out there, meaning that there's a link that goes down, then the blocked ports can now become re-forwarding or move to forwarding, and that becomes our redundant path back to the root. And so that's why spanning tree has a way of sort of healing itself. Now I'll just point out that in spanning tree, that can take a long time because we have to wait for the max age timer to expire, which is 20 seconds. And then we have to wait for listening and learning to go again, so they can be 50 seconds in a traditional or 802.1d spanning tree topology. And so that's one of the reasons why we say spanning tree is slow. Here's an example of a resolved topology. In this case, the root switch is in the bottom right. It is the root switch because if we assume that all of the switches have the same priority of 32.769, then that MAC address is the lowest MAC address. And so the path cost coming from switch 2, they'll both be zeros going up there. And then switch 1 and switch 3 would compare their two BPDUs. They would both have the same root. They would both have a path cost of 19, but switch 3 has a better transmit bridge ID, and so switch 1 has to block a port. So if you go right along the hexadecimal characters, you'll find out why switch 1 loses. And that's why port 3 on switch 1 is blocked. Just a quick note on priorities here. The priority always starts as a base of 32.768. And that's for Cisco devices, but a lot of vendors do the same thing. And the 32.769 is because we're 32.768 plus the VLAN, which in this case is VLAN 1. So 32.769. Okay, so spanning tree is really good. It gets you out of a lot of trouble, but it is, subject to technical issues. Like, it automatically figures things out for you. So if you don't do anything, spanning tree will give you a topology that doesn't have any loops in it, but it might not be the best topology for you. Everything is based on priorities and speed of the links. So that topology will be built, and it's up to you to go in and make sure that it's the best possible topology on that layer 2 portion of the network. It's also very slow for the same reason that I pointed out earlier. It can converge very slow, takes a little while, and then if there are topology changes, that can take a long time to fix. And then if you're in a situation where we have one change and then another change, it can really throw a monkey wrench into the way that spanning tree is resolving the topology. There were some early improvements like port fast, uplink fast, and backbone fast. Of the three, uplink fast and port fast are probably the most commonly used. Uplink fast is just a quicker way to fail over, and we'll see that Rapid Spanning Tree certainly adopted that one. Port fast is probably the most common because any port that's connected to a host doesn't really have to do spanning tree. It doesn't make any sense because you can't have a loop with a host. So in a lot of cases, we want ports to go forwarding much, much quicker. And the best example that I can give you is in voice over IP. When you plug in a voice over IP phone, it wants to get its configuration quickly. It wants to get an IP address quickly. And so if it has to wait for spanning tree to go listening and learning and then forwarding, it can take too long and things can time out for the voice phone. So for a lot of ports connected to hosts and special devices like phones, we do port fast, which means that it skips listening and learning and goes forwarding very quickly. Well, thanks for watching. Hey, subscribe and like if I helped you out there. And for right now, we're going to try and take a look at 802.1q.